You ever stop and think about the internet? I mean, really think about it. You've got billions of devices all trying to talk at once. How in the world does it not just collapse into one massive screaming traffic jam? It seems like it should be pure chaos, right? But it's not. And that's because there's this really elegant, invisible structure that's keeping everything running smoothly.
So, let's pull back the curtain on that structure. It's called IP subnetting, and today we are going to demystify it. We're going to see exactly how it takes that potential digital chaos and turns it into perfect, logical order.
Here's how we're going to do it. First, we'll look at the problem, what a single, noisy network actually looks like. Then, we'll introduce subnetting as the hero of our story. We'll get to know its essential tool, the subnet mask. Then we'll actually walk through a real example together. And finally, we'll wrap it all up with why this matters so much.
All right, so first, I want you to imagine a world with no subnetting, just one gigantic flat network. The best way to picture this is to think of a massive open-plan office. I mean, thousands of people, and not a single wall or cubicle in sight.
Now, in this office, if one person wants to talk to another, they have to shout, and everyone else in the entire room has to stop what they're doing and listen, just to see if the message is for them. Can you imagine the noise? That's what a flat network is like. It's a constant roar of digital chatter that creates massive traffic jams and slows everything down to a crawl. It is just incredibly inefficient.
And this is where subnetting swoops in to save the day. It's the simple but brilliant idea of taking that one giant noisy network and breaking it up into smaller, much more manageable subnetworks, or subnets. It's basically like putting up walls in that chaotic office to create smaller, quieter departments where people can actually get work done.
And doing this gives us some huge advantages. By keeping conversations local, inside their own subnet, you slash the overall network chatter. This, of course, boosts performance, makes the whole thing way easier to manage and secure, and it even helps networks stretch over really long distances. At the end of the day, it's all about one thing: efficiency.
So how do we actually build these digital neighborhoods? Well, the magic ingredient here is something called a subnet mask. I want you to think of it as the literal blueprint that tells every single device on the network exactly where the property lines are drawn.
You see, every IP address has two jobs. One part of it identifies the network. You can think of that like the street name. The other part identifies the specific device or host on that network. That's like the house number. The subnet mask is just a special 32-bit number that draws a line right down the middle and tells a device, okay, this part of the address is the street and this part is the house. It's that simple.
Now, back in the day, the internet used this pretty rigid system called classes. You had class A, B, and C networks, and each had a default locked-in dividing line. The problem was, this wasn't very flexible. You might get stuck with a giant class B network with over 65,000 addresses when you only needed, say, 50. It led to a ton of wasted IP addresses.
And that's exactly why we moved to a much smarter, more flexible system called classless interdomain routing, or CIDR for short. It lets us forget those old classes and customize the blueprint, drawing that dividing line with total precision.
And the way we write it is so simple. You just see a slash and a number, like /25. That number is just telling you exactly how many of the 32 bits in the IP address are being used for the street name part. So a bigger number, like /26 or /27, means more bits for the network and fewer for the individual houses. It's a really elegant shorthand for a powerful idea.
Okay, that's enough theory. Let's get our hands dirty and see how this actually works in the real world. We're going to take a standard network address and slice it up with a custom subnet mask. And don't worry, the math is actually pretty straightforward. We'll do it together.
So here's our scenario. We've got a network address, 192.168.10.0, and we're going to apply this subnet mask, 255.255.255.128. As we just saw, in CIDR notation, that's written as /25. Our mission is to figure out what new, smaller networks this mask creates for us.
And to do that, we just have to answer 5 simple questions. This little framework is going to guide us through the entire process step by step. No getting lost, I promise.
First question, how many subnets are we making? Well, a standard network of this type is a /24. We're using a /25. See that? We've borrowed one extra bit from the host part and given it to the network part. The formula is 2 to the power of n, where n is how many bits we borrowed. So 2 to the power of 1 is, of course, 2.
And just like that, we've done it. We've split our one large network into 2 smaller independent subnets. Nice and clean.
Okay, next up, how many devices can live in each of these new subnets? An IP address has 32 bits total. We use 25 for the network, right? That leaves 7 bits for the hosts. The formula here is 2 to the power of h for hosts minus 2. So 2 to the 7th is 128. And we subtract 2 because one address is always reserved for the network itself and another is for the broadcast address, the shouting to everyone address. That leaves us with 126 usable host addresses.
So there you have it. Each of our 2 shiny new subnets can support up to 126 different devices. Laptops, phones, you name it.
Question 3 is a big one. What are the actual addresses of these new subnets? For this, we need to find something called the block size. It's a super simple trick. You take the number 256 and you subtract the last interesting number in your subnet mask. In our case, that's 128. The answer is 128. That's our block size. This means our new networks count up in blocks of 128. So the first one starts at .0, and the next one starts at .128.
And now let's put it all together. This table gives us the full picture and answers our last 2 questions. Check it out. Our first subnet is 192.168.10.0. Its broadcast address is the number right before the next subnet starts, so that's .127. That means all the valid hosts are the numbers in between, .1 all the way to .126. Then the second subnet starts at .128. Its broadcast is at the very end, .255, and its valid hosts are .129 through .254. See how perfectly that works? 2 distinct organized digital neighborhoods?
So we've wrestled with the numbers, and we've got our answer. But let's zoom back out. Let's connect this back to that big idea we started with. Why is this organization so unbelievably important?
Well, what we did was go from one huge, noisy room where 254 devices were all trying to shout over each other to 2 smaller, calmer, more organized offices. This isn't just a math problem. This is how big companies keep their finance and marketing departments on separate, secure networks. It's how your internet provider efficiently gives IP addresses to millions of customers. By drawing these digital lines in the sand, we make our networks faster, more secure, and way easier to manage. We've literally created order out of potential chaos.
You know, subnetting is just one of these foundational, often totally invisible pieces of engineering that make our modern digital world possible. It really makes you wonder, doesn't it? What other elegant, brilliant systems are humming along quietly in the background, shaping the very structure of our connected lives?